No es solo el cine digital o digitalizado, sino que el término se refiere claramente a un cine expandido, a las modificaciones epistémicas, así como a las mediaciones.
Can you read this? More importantly, can you understand it?
If we can easily read a sentence without vowels, why do we need them? This is a question many of us have realized in the digital age. For example, it's like that we write MSG instead of message, or PLS instead of please in the text messages. If both are understandable, what's the point of adding unnecessary letters?
More importantly, how can we compress the information into its most compact form?
This is a very question was asked by Claude Shannon, a man who without exaggeration changed the world.
If today we can send messages beyond the solar system,
it's all thanks to this forgotten genius. At just 21 years old, the master's thesis he wrote at MIT in 1938 is still considered the greatest master thesis of all time, receiving the highest number of citations in history. Because the discovery he made with this thesis changed the world. He is the father of information theory, and he introduced us to a system where 1 plus 1 could equal 1, and in this way, the foundations of the digital world were laid. Despite this, almost no one knows or remembers him.
I know you're probably puzzled about how 1 plus 1 equals 1. I promise I'll explain it, but first, let's take a moment to see the journey that led Shannon to this revelation. Okay?
While still a student, Shannon started to study Boolean algebra at the University of Michigan.
In standard algebra, we work with numbers like 0, 1, 2, 3, 6, 9.
And in Boolean algebra, the variables are true and false, like 1 and 0, or heads or tails in a coin toss.
Heads or tails?
If you said tails, you're right.
I'm gonna toss it again.
If you said tails, you're right again.
Tossing a coin is actually like Morse code.
Instead of saying dash 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 dot, I can say heads 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 tails.
Heads or tails? Tails again.
Well, there is actually a reason why it always lands this way. Because both sides of this coin are tails. Yes, it's something that I prepared as a trick. So there is no randomness in this coin toss. I know the answer will always be tails. That's why we can't use such a rich coin to convey the information. It's just dot, 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 dot. I can't send the message this way.
We need to know that there should be another variable involved.
Alongside the dot, there should also be a dash for it to turn into information. So what about the something isn't reached, something normal? One side heads, and the other side tails.
When I toss this coin,
what comes up is entirely dependent on uncertainties. And the Shannon explains it like this. If everything is predictable, then there is no information. If randomness is involved, then you need information about everything. To understand what Shannon meant by this, we need to stop and think about it. Perhaps for quite some time. Shannon discovered that the way to explain communication using physics lies in entropy.
So he started to deal with uncertainty.
He says that the more uncertainties there are in a system, the more entropy there will be.
That entropy is a kind of measure of the uncertainties before I toss the coin.
For example, if I toss a coin and don't know what it will land on, the uncertainty represents entropy, and information is the knowledge I gain after tossing it.
If the coin is fake, that's both sides are tails, there is no uncertainty.
Therefore, there is no information gained after tossing the coin. But if we replace the fake coin with the real one, everything changes.
How many questions would you need to ask to figure out what's in my hand?
For example, if you ask me, is it tails? I can answer with yes or no, giving you the result. Yes or no, or 1 or 0. In a binary system, we can acquire information with just one question. Shannon wanted to name this binary system, so he combined the word's binary digit
and shortened it to Bit.
Yes, he was the first one in history to mention bit, the smallest unit of information. In physics, what the atom is to matter, the bit is to information.
Today when we use computers, we say 500 megabytes, 1000 megabytes. In those cases, the word byte means 8 bits.
Shannon's discovery is something we still use today. It's the foundation of compression programs.
For example, when we take a photo with our phones, its size might be quite large, but when we send it via WhatsApp, the size is reduced. That's exactly it. We compress the photo without losing its meaningful information.
Just like how I compressed the sentence at the beginning. It makes turn this into this. But how much can we compress it at most? For example, can we take 50 gigabytes of data and compress it down to 250 bits without losing any information? This is exactly what made Shannon famous in 1948. He discovered that there is a limit to transmitting information flawlessly, the Shannon limit.
And actually, this limit explains the essence of communication very well. To communicate accurately and effectively, we need the right tools and methods. Just like the speed of light has a limit, there is also a limit to transmitting information flawlessly through a channel. This was an extraordinary discovery and resonated widely at that time. But unfortunately, understanding it's as difficult as understanding why the speed of light is a limit. However, to make it intuitive, we can think like this. When we toss a coin, we need to ask only one question to learn the result. Is it tails? Only one question. Equals 1 bit. If I want to know the result of 3 coin toss in a row, I need 1 bit plus 1 bit plus 1 bit equals 3 bits. So how many bits are needed to express a sentence like the one at the beginning? For example, imagine we only want to transmit a single word from that sentence. You can think of it as a word guessing game. How many questions would we need to ask to guess each letter one by one? We are gonna think about that. For the coin toss, 1 question was enough. But how many questions would it take for letters? Do you have anything in mind?
One of the simplest algorithms to follow is processing by dividing by 2. For example, our first question can be, is this letter before M? If the answer is yes, we eliminate all letters after M. Then the second question can be, is it before G? If the answer is no, we eliminate all letters before G. As we continue to eliminate in this way, we eventually narrow it down to 1 letter. If we apply this algorithm to all letters and take the average, we find that we reach a letter in a total of 4.7 questions. This means a letter corresponds to 4.7 bits of information. This algorithm is the simplest approach and it's based on the fact that letters are distributed randomly with equal probabilities in our language. But we don't use letters in our language this way. For example, in English, the letter Q is almost always followed by U. Question, quiz, quality, etc. So there are some different ways or algorithms to predict the next letter. For example, if we know the letters is Q, we can choose U as the next letter without asking any questions. And this gives us a 1-bit advantage. The distribution of letters on our keyboards is already designed to optimize this. Claude Shannon calculated that we can find 1 letter in 2.62 bits in English. Look, the value dropped from 4.7 to 2.62. So we've achieved a smaller value than the 4.7 bits of random distribution.
And if we can use the rules of language to make its transmission more efficient, can we create a language that's even more effective for communication? Or can we find a way to make communication faster? Look, when Shannon was thinking about this, it was early 20th century. So the most effective means of communication were methods like telegraph or Morse code. Before the telegraph, for example, sending a message from America to England took more than a week because it traveled by ship. The telegraph was invented and this time was drastically reduced. But Shannon started to work on these ideas and imagined a way to make communication faster using electronic circuits. He conceived the idea of relays. The simple yet effective functioning of relays, being either open or closed, align perfectly with the fundamental principles of Boolean logic. A relay is either closed and conducts electricity, or open and doesn't conduct electricity. This binary state can only take 2 values, just like in Boolean algebra. Shannon, inspired by this similarity, demonstrated that it was possible to transform logical operations into electrical circuits. When relays are connected in series, they function like an AND logic gate.
Just like all the links in a chain need to be intact, all the relays connected in series must be closed for the circuit to be completed. That's why we show a series connection using multiplication. For example, if two relays are connected in series, both must be closed for the current to flow. 1 times 1 equals 1. If one of the relays is open, the current cannot flow. 1 times 0 equals 0. But in parallel connections, the situation is different. It functions like an OR logic gate and is represented with addition. It's enough for only one of the relays connecting in parallel to be closed for the current to flow. And that's why in Boolean logic, 1 plus 1 equals 1. At first glance, Boolean logic may seem contrary to the mathematical rules that we are used to, especially like how 1 plus 1 equals 1 instead of 2. But remember, this is not arithmetic, this is logical operation. Imagine you have a keycard to enter a building. However, you can also use a fingerprint scanner to access the building. If you have only the keycard, you can open the door. If you have only the fingerprint, you can still open the door. There is no need to use both methods at the same time. So the result is not changed if one of the conditions is 0. And the result is not changed even if both conditions occur at the same time. In any case, you will enter only once, not twice. So this is a real-world example of why 1 plus 1 equals 1 in Boolean logic. Boolean algebra is a clever way of transforming this kind of everyday logic into electrical circuits. In short, these complex integrated circuits we use today actually emerged from highly connected, open-closed relay systems. We converted analogy and logic into digital in this way. From this transformation, computers were born, then they shrank into cell phones and fit into our pockets. Thanks to the vision of a young mind like Claude Shannon, we have moved from communication through letters, telegraphs, which took a long time, to a communication that happens now in seconds. His unique perspective changed our world forever and ushered us into the information age. This is, I often wonder, what he would have thought if he had seen how information is used with ill intentions. I am sure Shannon, who has brought us to where we are today, never imagined a future where instead of recognizing him, we listen to the voices of fake scientists on television and social media every day. But just as we solve this problem, we'll also solve that one. Perhaps this is the great irony of information age. In a world we think we know everything, we have forgotten the value of true knowledge. Now, tell me, heads or tails?